Okay, there's a few more key point groups that I want to go through. Now, granted, this list from the textbook isn't exhaustive of all the point groups, but still, even though this seems like a slog, I want to make sure that we practice these symmetry elements. Okay, so this is the DNH point group. Okay, so again, n is going to be some number. For example, can you guess what this would be? D-Y-H.
This will just be D1H?
Nope.
No?
Look real close at what you got there. What's the principal axis?
Principal axis is the C3.
C3. So that makes this a D3H. So again, you're going to have everything has identity. You have a principal n-fold axis, n C2 axes, so a certain number of those, a sigma H, a certain number of sigma V planes, and one S sub n axis. And then of course for n equals 2, 4, 6, there's an inversion center. Now, well, these are supposed to be. Did I grab the wrong molecule? Let me double check. I'm gonna bring up Autobahn real quick. Oh no, that's fine. Okay, I don't know what I was thinking about because I was looking at that and I'm like, for some reason I thought there's an invert, but there's not. If you try to invert it, it would give you like a mirror image.
Sure.
It wouldn't be the same thing. Okay, so there, of course, you see the C3 axis, you see the perpendicular C2 axes, the sigma H plane. Now we also know if we have a C3 and a sigma H, that's going to give us our S. What S is it going to be?
Is it also S3?
S3. Also keep in mind when we get there, we have SNs and S2Ns. So you remember your S2N improper rotations are a higher order of symmetry. Pretty much all of your, actually for right now, let's just go all of your even numbers. So like your S4, S6, S8, so on and so forth. Those are going to be your S2N axes. That's what we're going to consider them for point group purposes. Then we go through and you can see your sigma V's and your S3 axes. So again, the sigma V's here, they're each going to go down one of the principal bonds. All right. This one's a little bit harder. The D and D point group. Now, okay, let's go back up. If you look here, you see how this is D and H, so some number H. That means we're really defined by that principal axis and the sigma H reflection plane. What do you think D and D is going to be governed by?
Is it going to be those D, the ones that cut down?
Yeah, so this one of course will be governed by your dihedral. Yeah, so your sigma V's that actually become sigma D's because they're the dihedral reflection planes. Remember that so remember H is horizontal, V is vertical, D is dihedral.
Okay.
And they're of course those are the reflection planes that are going to cut through C2 axes. So I have this position in two different ways. So this is ethane. So look at it really carefully. Can you tell me what the structure of this ethane molecule is?
The structure of it?
Yeah, I don't know if you've covered this in organic yet. So have you done the structure where you go?
Oh, where it's like they're up. Oh my gosh.
So have you done this yet where you have C?
Yes, we've done that. I just can't remember the name for when they're like fully spaced out.
Yeah, that's a horrible circle. So you get this. And it's like you're looking right down. So the one on the right, it's like you're looking right down the center. This is called the staggered configuration.
Staggered. Yeah, that makes sense.
So that's something you want to remember for organic chemistry. Now, if this is staggered, you know what it would be called if I twisted it and lined up the hydrogens?
Oh my gosh.
It has an astronomical term.
Yeah, it's like eclipsed.
Eclipsed, yes. So this is the staggered configuration. Okay, now the C2s are a little bit harder to see, so I actually want to go to the outer bind so you can see that rotation. Now you can see, of course, they're perpendicular, but how do they actually rotate? Some of these C2s are hard because if you look at that staggered configuration, it's got to do some kind of rotation and then flip so that it gets the hydrogens in the right place. Okay, this is our DND. Staggered. Okay, so let's bring up our C2 axes. So let's just look at this one, okay? You see how it's actually kind of like a little bit off center from any one of the bonds?
Mm-hmm.
So what that's going to do, so yeah, it's actually doing like a little bit of a rotation. Let's try and get that straight up and down so we can see it. Okay. And it's just putting those right in proper locations there. There's another one. There's another.
Yeah, they don't like seem to quite cut.
Yeah. Yeah, they're
see
just, they have to be in a location where they're going to flip it in a way that the hydrogens will end up in the same places once you flip it.
Mhm.
So again, some of these axes are, I think, are the hardest ones to see, hardest ones to, and that's why I want to practice these to the point where it's like ad nauseum. Then, of course, look, we have explain this an S6 axis. Why is it an S6? It's 360 divided by 6. So we're not doing, so a full S3 would take this hydrogen and move it there. But that wouldn't give us our S plane.
because it's just because of that rotation and they're like halfway in between each other.
So this hydrogen here has to rotate to halfway in between, then it can reflect down into that hydrogen. So some of the, again, once you see them, it makes sense, but they can be a little bit more difficult to really kind of think about. Let's see. Okay. And then, of course, there's your sigma D planes. So remember, sigma Ds are sigma Vs. It just depends on if they're cutting between those C2s or not. So if we go back to the Otterbein and look at that, get rid of those. Well, no, actually, I put them in there. Tip that up. Let's see how that cuts right between those.
Yeah.
If I did all of them, it'd be the same thing. So of course that is what we, so that's like the definition of a sigma D.
Mm-hmm.
We're getting higher and higher in symmetry. Here's a very famous one, the TD group. Tetrahedral symmetry group. Let's spend a minute or two. Tell me what kind of symmetry elements you can see in here.
Gosh, could you put one down each bond?
You could. So that would give us a principal axis. What is it?
Okay.
I positioned it this way so you can see it better.
C3.
C3. So of course, then we're also going to have a unique C2-3. What else do you think we have?
You'll have sigma Ds for all of them, right?
Mm-hmm. And why do we have sigma Ds?
Because it can cut down the middle of each of those.
Mm-hmm. So like, let's say I put one right there. Oh, what kind of axis is that?
That one's also C3, right?
No, it's not.
No?
Nope. If I rotate here, what's going to go where?
Wait, is it going straight down that bond?
No.
It's halfway between those two.
yeah, so just look at
Oh, so
the,
at C2 then.
yes, it's a C2. So then, of course, we have several of those, which leads us to having sigma Ds. And then, oh, there is an improper rotation.
An improper rotation.
Mhm. So again, kind of tip it up.
Yeah, like it's
So let's redraw it here. More traditional configuration. So there. So of course, there's our C2.
and then can you put like one that's parallel to those two top hydrogens? Like a plane there? Do I know what I'm talking about?
I think you do. I'm just trying to grasp what you're saying.
Like I don't know.
So well, let's think about the improper rotation. If I'm going to put a reflection plane in the center. Okay. How far would I have to rotate it to get those to then reflect and make the same molecule over again?
90 degrees.
90 degrees, which makes it a what?
S4? S2?
S4.
S4.
Because again, your C2 is going to go 180 degrees. Your C4 would go 90 degrees. So you want that 90-degree rotation, then a reflection, you get an S4. So let's take a look at some of these. So yeah, so like you said, we have C3s down each bond. And then you see all the C2. So then I've rotated it. So you can see all the C2s that are going to take hydrogens. So it's going to take there to there, there to there, stuff, over and over and over again. And you can think of, I can rotate this methane molecule any way I want to put any two hydrogens up. And that's why we have all these different C2s. Now, here's your sigma Ds.
Ooh.
I gave you an example of at least two of them, but then you see that you end up with a total of 6 of them. I gave you 2 so that you can kind of see what they're looking like. And then there's your S4 plane, your S4 rotation. It gets worse though.
Yeah.
The octahedral symmetry group.
Okay.
This one I'll bring up on Otterbein so we can kind of look at it piece by piece. You have C4s, C3s, C2s. So let's kind of think about that. So the C4, you can see the C4 if I rotate it in the traditional octahedral representation. That makes sense.
Yeah.
Look at the C3. Does that make sense to you?
Yeah, I can see it because they're all going up.
Right. If I put the 3 groups up, I have to rotate through a C3 just to get it back to a indistinguishable representation. And then of course, if I rotate it onto its what I would call its side, because its axial positions are horizontal now, you can see the C2 because you get that nice square around the middle. And it's kind of like those 2 hydrogens sticking up on methane. You have to flip it 180 degrees just to get it back to where it was. What else does this have? So it does have a sigma H. How many of those do you think it has?
Mm-hmm. Is it just the one?
Nope.
No.
You see, then try to flip it on its side, see if you can see anything.
Yeah, so I guess it'll have 6 of them? Maybe? 3?
3.
Oh, because they'll be the same thing.
Uh-huh.
Okay.
The sigma Ds, that one you have 6 of those. So if we put in all the C2s, it would end up with 6 of those. And then you have 2 improper rotations. The S6 is a little harder to see. Because again, you see those 3 that are up, you see how each one of those goes in between the bonds with the 3 on the bottom. So I'm going to have to rotate through a C6 and then reflect. Granted, C6 is not actually a representation, symmetry in this molecule, but that's essentially what we're doing. We're doing a C6 rotation, then reflecting. Mm-hmm. And so that gets you your S6. The S4 is a lot easier to see because that takes in the C4 axis.
Yeah.
Now here's a question. How many S4s does it have?
Is it also 3?
3. Mm-hmm.
Constitutional.
Oh yeah. This one is no fun. No. To understand some of these, first off, look at that first image. Do you see how you have the pentagon on one side, and then the pentagon on the other side is rotated the other way?
I see that.
So that's important. So it makes sense, for example, that you're going to have a bunch of C5s. Okay. But take a look at those C3s. I tried to rotate it in a way. Can you see the structure that dictates that that's a C3?
Is it like the pentagons on the sides? Wait.
Kind of. Look at where the C3s are.
Yeah. Okay.
So the C5s go right through the center of pentagons.
So it's going down those little hydrogens coming out of them.
Mm-hmm.
Can we look at this one in Otterbot?
Oh yeah, because you take a look here.
Mm. They're all little tetrahedrals.
Mm-hmm. The fun part is there are also C2s that kind of go diagonal. So you see it's going through this bond, then through that bond, and that C2 will actually give an indistinguishable configuration. Now take a look at that one, and that's 10. Now, okay, if we have a C5 and that rotates each atom around the pentagon once, okay? But you remember, this is why I told you to think about how the pentagon on the bottom is rotated the other way. Mm-hmm. Now, if I want to rotate and then reflect and get the exact same thing, do you see why it has to be S10?
Yeah, it has to be half of the
distance. So like this atom here has to go to there, and then it reflects to that carbon there.
Yeah.
And so on and so forth. So it has to go half the rotation of a C5, so it's going to have to be a C10, then a reflection. There are also S6s. So we go back to the C3 bond, and again, the C3 on the bottom. So you see here we have a bond, and on the bottom we have an angle. On the bottom we have a bond. So again, same kind of rotation. So we're going to have to do half of the C3, then reflect. And then let's see. Yeah, the sigmas we're just going to have, and these are too complex to actually be V's, H's, or D's.
Sigma.
Yeah. So let's take a look at this. Yeah, icosahedral is. I'm never going to give you any of these, but you have to know they exist so that you can make sense of them when we get to point group or assigning clusters. Which one did I use? There it is, the dodecahedron. So it's a fun little ball. We could have used the traditional buckyball.
Oh, that was cool too.
These are actually structures that are made in lab. So these aren't just somebody's imagining. Buckyball's really been.
Yeah, they look like a soccer ball.
I don't like the ones that are just geometric structures because it doesn't seem to really apply to a molecule to me. A snub. Yeah, let's not do that one. We're going to use the ones that are actual molecules. Your dodecahedron here. Okay. So first off, yeah, look at all those.
Okay.
So we'll just do that one, okay?
Okay.
There's your C5. And what did we say is C5 minus 1 is?
It's like the opposite direction.
Yep. And we'll get to that. That's part of group theory. Okay, so it says 12. We're not talking about the reverse directions right now. We know that they're there, but so technically that's 6 C5s. Again, the C25, exact same thing. It just goes 1, 2. So same idea. C3 rotations. That's okay. There's one. Okay. Now, first off, do you see how, again, we have that angle there and then a bond there to match up to kind of split that angle?
Yeah, it's not
That's
straight up and down.
Right. That's why we have that S6 rotation. So again, if I just take that, there it is. That's why you're able to use that little tetrahedral shape as your governor for the C3. C2 rotations. These are the hard ones. So, okay, this one's easier. It's easier to see if you look at it as just straight up and down. Okay. Okay. So there it is right there. All right. So it just, and again, the way we can do it is we can look here, down that bond here. Right there, that is a C2 symmetry. The inversion center.
Oh.
So it has one.
Yeah.
S10 rotations. Okay. So again, we rotate halfway around and then reflect. And straight up and down. Okay. So these last couple of point groups, your THTD, your octahedral, your icosahedral, these are going to be your high symmetry point groups. That's why they have so many operations. So again, S10-3, so 1, 2, 3. Okay, there we go. S6 rotations. Oh, 2. Fine. Want to do that? We'll do that. Okay. So again, we're going to go down that same axis as the C3. And then, but it's just going to go halfway between and then reflect. 15 of them. If I put them all in.
Oh, wow.
That's why I only gave you a few of them. So
it looks cool.
It does. So let's just look at this one, okay? I mean, there are C2. We're not even going to worry about that because these are just too complex to really be described as VH or D. So this one, of course, is just going to reflect like that. Because, I mean, I could start putting in C2s. I might be able to, I don't know, it's in the plane. I guess maybe it cuts those, but then, of course, there's going to be principal axes in there. But then there's also, it's really too complex to go, well, which one is it?
Yeah, I don't know how you assign, like, this is the principal axis.
Yeah.
For something like
well, for other ones, it's easy. It's the highest. It's the highest order for C. Whatever the biggest n number is, that's your principal axis. On this, there's so much symmetry here that it becomes a bit overwhelming. So they're just called sigmas, and there's a total of 15 of them. So yeah, again, you put them all in. Yeah, it's a little interesting. It's just so. That is your icosahedral point group. Okay. Now we've done a bunch of this. So what we're going to do next, point group determination. So I've given you two of these. I kind of like this flow chart, but I also gave you the one from the book. You can use both of them. So I want you to take a few minutes and see if you can tell me what point group this is.
Okay. Is the molecule linear? No. Does it have two or more? Good. Okay. I don't think it does. It does not have more than two. It doesn't have two or more. Right?
Well, let's think about it.
No, I don't think so.
Does it have a CN active?
Yeah, his CN.
Yeah, so it doesn't have two or more, so that's a no.
What are there NCTs perpendicular? No, there's not.
Right.
Is there a horizontal mirror plane? No. Are there any vertical mirror planes?
So ask yourself where the principal axis would be.
It'd be down the fluorine to the
Right.
chlorine.
And the sigma V's have to incorporate, they have to be incident on that,
Yeah.
on
So
that.
I guess you could have vertical
Mhm.
mirror planes. So would that make it
It's a little smaller now, but
CNV?
yeah, but what would the N be?
C2? Wait, 3.
C3V.
C3V.
This is a C3V point group.
Okay, okay.
So remember, the N is going to be dictated by your principal axis. So let's see what we have. The C3 there. Does it have two or more of those? No, it doesn't. So go here, go here. Are there C2 axes? I mean, I could try a C2 axis along any of the radial chlorines, but that's just going to put the chlorine up and the fluorine down. It's not the same. So that's got to go with a no. Are there horizontal mirror planes? Well, if the horizontal has to be perpendicular to the principal axis. So if we go like that, I mean, it's not going to work.
Yeah.
So that's a no. Are there vertical axes? Okay, well, if I say, well, let's just do the easy one here. Yeah, there's definitely sigma V. So it has to be a C3V point group.
Okay, question.
Mhm.
Wouldn't the fluorines and chlorines not have like an exactly equal like angles?
They wouldn't, but to really get this, you want to go with the ideal structure. Because in the laboratory, even though the fluorine, for example, is going to kind of push those chlorines away, you're still going to get reactions in the lab that are part of this point group. So figuring it out using the ideal structure still gets you the same chemical reaction based on the symmetry. And so especially when you're looking at spectroscopy, you're still going to get the same kinds of vibrations.
Okay.
Let's use the flow chart from the book. What do we think about this one?
Okay, start here. Is the molecule linear? No. It is none of those. Right? No, that's not octahedral. Is there a principal axis? Yes. Are there perpendicular? Yeah. Is there a H point? Yeah. So it's D3H?
D3H, yep. No, I didn't expect you to get those that quick.
I like the flowchart. It makes sense.
Yeah, so these flowcharts are helpful. I have a hard time with the one from the books you see in the upper left. It just says, does the molecule have high symmetry? Well, yeah, but then you're going to have to just kind of know if it's TD, OH, or IH.
Yeah.
Which isn't necessarily helpful. I like over here where, let's see, where are those?
Yeah, I can see the OH.
Yeah, so it kind of helps you get to them.
Yeah.
So I think using both of these is inevitably going to be helpful. We want to make sure the reason okay, where is it? One of these should have here. that's why I wanted to talk about what an S2N versus an SN is, because S2N is going to be on the flow chart. How about a harder one?
Okay, molecule is not linear. Does it have two or more seat and axes? Oh my gosh. I think it does, definitely does. Right, because I can go, no. It doesn't have two or more.
No, so it has at least one.
It has at least
and
one.
what is that axis?
It's the C5.
C5.
Okay. And then
Here's a question. We were looking at this. What's the hapticity of this molecule?
hapticity,
Uh-huh.
5.
5. Because again, each one of these carbons simultaneously bonded to the atom in the center.
So it's like the hapticity of that little pentagon.
Yeah.
Okay. Are there NC2 axes perpendicular? I don't think there are. Is there a horizontal mirror plane? Yes. So C5H? No. That just doesn't feel right.
Nope. There's one that you missed.
I guess you can have the perpendicular axis, can't you?
Mm-hmm.
It's just C2. It's not greater.
Right.
Okay. Is there?
So then that's a yes.
Okay. And then horizontal mirror plane. Yeah.
Well, careful. Let me bring this. Well, that would be the answer.
Horizontal mirror plane.
So that has to be perpendicular to the principal axis. But do you notice how this? So look here. It doesn't exactly hit, does it?
Oh. Okay.
This one's very subtle.
Okay, I see.
They're off. They're skewed just a bit.
Just slightly. Okay. Are there dihedral mirror planes? That's the one where I get to rotate it a little bit, right?
Yeah.
So is that a guess then?
So no, there are no dihedral. We're gonna look at it on Otterbein.
Okay.
So you have the DN, which make.
I might not remember what a dihedral mirror plane is then.
Remember, that's the one that splits C2s down the. So
Oh, so that would be straight up and down.
yeah. So it has to be a sigma. So a sigma D has to be a sigma V. So it has to include the principal axis, but then it has to split C2s elsewhere in the molecule.
Okay. And we can't do that.
Right.
Yeah, because those little hydrogens aren't perfectly in line. So it'd just be D5.
D5.
Okay.
So you see, it does get a bit harder.
Yeah.
But if we look here, now you're starting to see all of these here. So your point groups, your D5, again, you see how those are slightly off?
Yeah.
That's what changes everything.
Okay. Okay.
So you do have some C2s, but you have no sigma Vs. So if there's no sigma Vs, there can't be any sigma Ds. So you see how that it's at like a weird angle, but then it rotates it in a way that puts it right back where it is. Some of these and a lot of these molecules you're looking at, these are one of the big things that you get in inorganic chemistry is crystals. So a lot of these are from crystal structures. Maybe at some point we'll look at the symmetry of a perovskite.
A perovskite?
Uh-huh. Perovskite structures they're actually pretty important technologically.
What are they used for?
Well, let's see if I can find one. So that's really, really small. Okay. Let's just structure. They're using solar panels for one. So this is your basic idea here, like this kind of structure. Again, so you could look at them like that, but a lot of these materials, they have unique electron transfer mechanisms, so they're great for solar panels. Some of them form lattice structures that have micropores in them. So, for example, they can be used to capture biological or chemical agents because the molecules will get stuck in with so the micropores will have van der Waals effects. The compound enters the micropore and they get stuck.
Right. So like a filtering system or something.
So there's a lot of uses for them.
That's cool. Perovskite.
So yeah, a lot of these are going to be crystal structures. Okay, let's try. This one should be a bit more straightforward. I just want to try an exercise using the book's flowchart.
Right. It's not linear. I would not say it's tetrahedral, icosahedral, or octahedral.
Nope, it is not.
Is there a principal C and axis? That'd be like straight down the sixth thing. Are there NCT? Yeah, because you go down those oxygens for each one. No. Because those little side oxygens make it.
Yeah.
Okay. So that's a no. Is there a sigma H plane? Yes. C3H?
Yep.
Okay.
And again, like I said, this becomes important when you get into a laboratory because these symmetries, molecules that fit in these symmetries, are going to have they're going to have predictable reactions. So even though this might seem a little superfluous right now, going, why are we working on all the symmetries of these? Well, it affects how they work in nature.
Sure.
And so once you get a better grasp on symmetry and reactivity, this is going to be real important. Now, so yeah, we're probably going to end a little early today, but you got that way quicker than I did when I was in your position. But trying to remember the teacher I had, he jumped. Oh God, what did he do to us? He jumped straight to things like this.
Oh.
So I was sitting in there going,
yeah.
it was like day 2 of symmetry, and he goes, "What's the point group of this?" I go, "I don't freaking know."
I don't know.
So yeah, but you got that real quick. Okay, so I'll make sure to have more for you as we go on. Okay, so point groups come from what's called group theory. Okay, so there are 4 main rules to group theory. Each group must contain identity. Well, like we said, that's simple. Here's a molecule, don't touch it, identity. Okay.
And that's the E that we're talking about.
Yeah. Each operation must have an inverse. So you remember those, like the -1s we were looking at?
Yeah.
That's where they all come from. That's the group theory. So if you have 6 C5s, you have 6 C5 -1s. So that's why they say there's 12 C5s. That's why Otterbein says that. It's bringing up the group theory. The product of any 2 group operations must also be a member of the group. We'll look at that. And the associative property must hold. Now, let's think about how this works with symmetry elements, okay? You see your C3 times sigma V prime?
Yeah.
So here, if I had a molecule, and the way you do this is as you're multiplying, you do the symmetry operation left to right, okay? So in this one, on the left, I would do the sigma V first, then I would reflect it through the sigma V prime, then I would C3 it. That should equal me being able to C3 it first, then sigma V it, then sigma V prime it. Okay?
Yeah, you'll get the same molecule.
Right, you'll get the exact same configuration. Now, let's look at point number 3.
Okay.
Okay, so I want to use ammonia. And let's just say we're looking straight down on it. Okay? Now, if I take it through a C3, let's do it counterclockwise. What's going to happen?
It's gonna end up in the same positions.
It will be.
One, so it'll be like,
It will be indistinguishable. Let's work with H1, H2, H3.
so H3 will be at the top,
Right.
H1 at the left.
Now, and I'll show you where this is. What we're going to do is we're going to do a sigma V double prime. Okay, and that, let's just say, okay, let's just say the sigma V double prime is there. Okay, so what's going to happen now?
We're gonna like rotate it, like flip it like a pancake, question mark?
Yeah, pretty much.
Okay.
So the H3 stays where it is. What do the other two do?
H2's on the left now and H1's on the right.
Oh, yeah, I'm sorry. And I did that wrong. That's not H3. That's H2. There we go. So now H2 is there. H1 is there. So as you remember, you remember that this is then C3 times sigma V prime, double prime. Okay. So that is the multiplication, the product of two symmetry operations. Now, let's start with the same configuration. Okay. And what we're going to do this time, we're going to use the sigma V prime. Now what happens?
The H1 and H3 will swap this time.
Mhm. And so you notice that this obeys the group theory rule that your C3 sigma V double prime product equals the single sigma V prime. So that's a rule of group theory. The product of any two elements of a group must be another element of the group. All right. Do what?
When you assign them as sigma V double prime versus sigma V prime,
Yeah.
we're like, why?
Because right now, so we can differentiate.
Okay.
That way, because otherwise it'd be C3 times sigma V equals sigma V.
Yeah.
I want to differentiate right now to show that each one of these, even though they're equivalent, would all technically be sigma Vs. I'm like, okay, well, they're going, now that we have H1, H2, H3, I'm just going to call them sigma V prime, and then so V would be on through hydrogen 1, prime through hydrogen 2, double prime through hydrogen 3.
Okay.
I'm just using this to denote the difference, and so you can actually see the multiplication of two different elements equals another element.
Okay, I get it.
Yep. All righty. So I've been telling you, and most people in physics look at me like I'm speaking gibberish. Matrices. So we're going to be using matrices to understand where character tables come from. Okay. Character tables, again, they're going to be just like they said, they're going to be a table of symmetry operations. They're going to be specific to a point group. And so you're going to be able to see the types of symmetries that are available to molecules in that point group. Okay. So you know how I've been telling you that matrices are actually kind of a map of a space that you're living in?
Yeah.
So this is an example of what I'm talking about. Imagine you have vectors A and B living in a certain space. That space is defined by X, Y, and Z. So this is how the vectors in that space will fit into a matrix. So you can start to get an idea of how this matrix becomes a map of that space.
So literally just the X component literally just gets put into that little space. Okay. I see.
Now, otherwise, they're just going to be these groupings of numbers. Okay. But I want you to start seeing them as maps. because when we look at rotation matrices, it'll make more sense. It's like, well, I have this molecule aligned along X and it gets a -1. That means it flips from here to here. This molecule, this atom aligned along Z, it gets a +1, which means when I do the rotation, nothing happens to it. So I want you to start understanding these as maps that define a space. Okay. Now, the first thing we have to do is matrix multiplication. So this is your formula for matrix multiplication. This is gonna start to make more sense when you read things now. So you see each one of these has a double subscript.
Yeah.
So for matrices, your IJ, your first one is your rows, your second one is columns. Okay. So take, for example, let's just say I had a 2 by 2. Okay. So what do you think 2 by 2 means?
It's like 2 values this way, 2 values that way.
Yeah, well, it's 2 rows, 2 columns.
Yeah. Okay. Yeah.
So 2 by 3 would be 2 rows, 3 columns, so on and so forth.
Okay.
So imagine I had a Cij. So what I have are C11, C12, C21, C22. So that's what the IJ means. So it's the location of each individual value. So your C11 is at the row 1, column 1 position. Then you have the C12, which is in the row 1, column 2 position, so on and so forth. That's what the IJs mean, is telling you the position of the elements. Now, I think the best way to really think about a multiplication is you take you take the row of your first one, multiplied by the column of your second one, and you're going to add them together. So let's do the multiplication. I'm going to show you how this works, because I want you, whenever you multiply them, your K's have to be the same, or you can't multiply them. Okay, so if I have 2 columns in the first one, I have to have 2 rows in the second one. Okay, or it won't work. So what you get, this one is rows, columns, and this one is columns, rows. Okay. Now I'm going to show you how this works, and I want you to, because you see the sum. And then I want you to think about this, and make sense in your head of how what I show you fits with that formula. Okay, so at the row 1, column 1 position, I'm going to do row 1, row 1, column 1. Okay, so what I'm going to have is I'm going to have 1 times 7 plus 5 times 4. Okay, so I just multiplied and added the elements of row 1, column 1. So now let's go to row 1, column 2, and that's going to be 1, 3 plus 5, 8. Okay, I just multiplied and added row 1, column 2. Then we'll do row 2, column 1, 2, 7 plus 6, 4, and then finally row 2, column 2, which is going to be 2 times 3 plus 6 times 8. And we get our new Cij matrix. Oh, shoot, I did. Oh, 20, so 27. I don't know. Go through and fill those up, because I didn't do it. Then we're out of time anyway. But this is how you put it together.
Okay.
Okay. So just remember, you're going row, column, row, column, row, column. So go back through, look at this formula for matrix multiplication, and work on making sense in your head of how this fits together.
Sure. Okay.
Okay.
Yeah.
And then we'll continue from there.
I've definitely done this before. I just do not remember it.
Yeah, well, it make linear algebra is a whole new thing on its own, so.
Do they even have a linear algebra class here?
They do.
Whoa.